Hello everyone, welcome back to Code for Teachers. I'm Michael Taggart and this is Chapter 4, Section 1, Functions. I've been really looking forward to getting to this section. I think that functions are some of the most fascinating topics in computer science. But let's start with a basic definition. Functions are mini programs that we can refer to again and again. If you have some code that you need to implement time and time again, we can wrap them in a function and use them rather than copying and pasting all that code. Functions take these things called arguments. They're like mini variables. We sometimes call them parameters as well. And those arguments or parameters inform their operation. This is just like in math. Now, something that's slightly different as a concept in computer science and programming functions and mathematical functions is that functions can and should return information. They should have an output in programming. In math, they always do. But there are certain kinds of functions in programming that don't explicitly return information. They perform operations, but they don't return information. When we're building our functions, as we'll see a little bit later, we should follow the SRP, the single responsibility principle. And so functions should do one thing and one thing only. We don't want to mix our concerns. So functions allow us to separate out the different pieces of our program so that we work on one thing at a time. Let's take a look at functions in math versus functions in Python. So just in case anyone is not familiar with the syntax of functions in math, we have this function called f, and it takes an argument x, and we set it equal to 2 times x plus 3. So that's the definition of the function f. Now if I call the function f, I invoke it by saying f and then I give it the parameter or the argument 3, what I'm saying is 2 times 3 plus 3, which of course is 6 plus 3, which then returns 9. Let's look at the same function in Python. So our first line uses the keyword def, and that tells us that we're defining a function. We're going to name it f exactly the same way. And in parentheses, we see that it takes a single argument, x, and then a colon, delineating that we are, in fact, beginning a function definition. So, like all other delineations in Python, we're going to indent the next line. Now, this is a nice one-liner. All we need to do is return 2 times x plus 3. Python understands order of operations, so even though I don't have parentheses around the 2 times x, it should still work out. And when I call f of 3, it will return 9. Now each piece of this has a specific term, so let's make sure we know those. The first line is that function definition, also sometimes called a function signature, but this is not exactly a function signature because it's not telling us explicitly what data type it's returning. So this is the function definition on that first line. The second line, or anything inside of the function itself, is the implementation. It's the actual details, the nuts and bolts of how the function does what it's supposed to do. And then here we have the function call. So it's important to distinguish the function definition from the function call. When a function is defined, you're telling the computer what to do when you invoke the function, but it's not actually invoking the function. Sometimes I tell my students that, from a Harry Potter perspective, this is writing down the spell, not casting the spell. So let's go and try a function. Okay, here I have a function that I've named double, and what I want it to do is take a number n and double it. And I have return none, that just means that I haven't implemented the function yet. And I have some other pieces down here that we'll get to in a moment, but this double function is exactly what I want to work with now. Now, luckily, double is a really simple function to implement. All I have to do is multiply this number n by 2, and that's going to be the return value. That's going to be what the call of double returns. So if I say n times 2, I've done my work. Double will actually function already. Now, beneath it I have some work that I want to do. I have this list nums, which is 1 through 10. And I've asked, is there a better way to state this? There is, and it involves some built-in functions in Python. We'll put those in at the end of this little bit. and then I have this empty list doubled. And what I want to do, if it's not clear, is I want to create a list of all of these numbers doubled. So let's write that loop. Let's write a loop that goes through the list and adds the result to doubled. So I'm going to say for n in nums, and I'm appending to the list, of course, so I say doubled dot append. And what am I appending? Well, I'm appending that n doubled. So what I'm going to do is I'm going to call the double function inside of my append, passing that n to it. Now, this is a little bit misleading because I have an n here that I use, which is short for num in nums, and then I have an n here. So I'm going to modify this just a little bit to say for num in nums. And when I say doubled, I'm going to say doubled num. Now, what's going on here? So I'm appending to the list doubled. What am I appending? Well, I'm appending the result. Oh, I'm sorry. There we go, double. I am appending the result of the double function when given that specific number. So on that first run through the loop, num will be this integer 1, and I'm going to send that into the double function. Now inside the double function, that 1 is going to be assigned to this argument n, that variable inside the function. So it'll be 1 times 2. The next time through the loop, it'll be this value, which gets passed as num over to this n, and around we go. So let's run this and see what happens. So I get the list 2, 4, 6, 8. So I've doubled those numbers. And just for a little bit of cleanliness, and rather than having to print out this whole thing, remember that range function that we use to create loops. Well, I can also do range 1, 11, and remember that that's a range object, and I convert it to a list just by wrapping it in a list conversion, just like we do strings or ints. And that works exactly the same. It's just a little bit cleaner. Remember that range takes either an endpoint or a start and an endpoint, and that endpoint is non-inclusive. So it still goes 1 through 10. Now, if we really wanted to, we could actually create another function, right? Wrap all of this inside another function. And we're going to do that. We're going to create a new function called double nums. And it's going to take one argument, which would be nums. And then inside, we're going to take this doubled and this loop. We'll leave this out here just for the moment. Now, if I wrap this in a function and I want to use it appropriately, I have to return something. What am I returning? Well, I've got this answer list here, which I'm appending things to. So I'm going to return doubled. Let's change this variable nums a just so we're clear about variable names and argument names. So now what I'm going to say is I'm going to print the result of double nums a. But this is where the usefulness of function comes in. If I make a nums b and say list range, and let's say we go from 20 to 31, right? I can have 2 lines, one of which prints out the result of doubling nums a, and another one which prints out the result of doubling nums b. So without having to reuse or retype the same code, I've been able to use this function multiple times to get the results that I want. So this is a new structure in our programming, and it might seem like a little bit more work to wrap everything, containerize everything inside of these functions rather than just writing our set of instructions and using the loops and conditionals we know. Why use functions at all? Well, functions do compartmentalize our code, and that's really important because as our programs get more and more complex, we're going to want each single piece, each single behavior of our program to be testable. And that's also why it's important that functions return values. What we're testing when we test our programs are the return values of those functions. This follows the single responsibility principle. We want our functions to do one thing only so that if it does go wrong, we know exactly where something has gone wrong. Another way of saying the SRP is do one thing and do it well. As we write functions and we're very careful about naming our functions, it's going to make our code very readable. You can imagine that having named functions whose names represent their behavior would be easier to read than a list of instructions that may be very, very complex, and it's not exactly clear where you're going to end up at the end of all that code. One of the really powerful things about functions is if we are careful about our input types and output data types, and we're making sure that functions return values, we can compose functions for incredible effects. So you can have, we saw this already with range and list, or printing the result of double nums. We're composing functions together rather than having a whole string of other pieces. I think that functions are also a really clean mental model of programming. It's the input-output process in microcosm. So you have arguments that go into a function, and at this layer of abstraction, what the function or how the function is doing what it's doing doesn't really matter. But we think about the arguments going in, the data type of the arguments going in, what we need, the function, what it's supposed to do, and how it outputs its result. And if we think about programs in that way, it's very easy for us to put the pieces together and take large problems and break them down into smaller problems that we can solve using multiple functions. I like to think of functions as the atoms of programs. So our other control structures and keywords would be, I guess subatomic particles, electrons, protons. Now this is a style of programming, and it's not the only one. Obviously, if you're listening to this or watching this, you're going to get some of my programming style bias. And I tend to write in a mostly functional manner. Functions are necessary for any kind of complex programming, but thinking of programs as combinations of functions isn't necessary. There are other ways to envision your program structure. But I would recommend thinking of functions as the building blocks of a program. And that's in distinction from thinking of programs as a set of instructions. So if we think of programs as a set of instructions, which is perfectly valid, you're always thinking step by step by step. But if you start thinking about programs as sets of functions, you begin thinking about how we transform information from one state to another. And the reality is that programming involves both. But they are different ways of thinking of solutions, and it's important to know that as a programmer and as a teacher, because different approaches may not only make sense for different problems, but also may make sense to different students. I've had students who really struggle with procedural programming, but absolutely connect with functional programming, and vice versa. Okay, that's it for this lesson. In the next lesson, we're going to go into